Can you hear me now? Hello? You can hear me now?
Yes,
Yes,
we
your
can
voice
hear
is
you.
very low.
Okay, thank you. Thank you very much. Sorry for that. Now doing very good.
Hello, sir.
Yes.
Your voice is not clear. It's very low. We can't hear you properly.
Okay, let me adjust.
Okay.
Okay. Mic testing. Mic testing.
Yes, we can hear you now.
Mic testing. Mic testing.
We can hear you, sir.
Mic testing. Mic testing. Mic testing. Students, sorry, I hope you can hear me now.
Yes,
Yeah, we
clearly.
can hear you.
Very sorry for that. I think my sound system got messed up, but I have gotten note of Dukan Lojore's concern. I'm going to correct that. So let me very quickly go back to where we were, so that I can we can continue. And very sorry for that. So Lojore, I have corrected your issue.
All right, thank you, sir.
Are you Lucy Lojore?
Yeah, that's me.
Yes, I have corrected that.
All right, thank you.
Okay, so let me continue then so that we can finish. We had explained some trends. So here is when I was explaining what happens in groups 2A and group 5A. And the statements are here. All group 1A elements have moderately positive electron affinities, and group 2A elements have lesser electron affinity compared to group 1A. And I explained that when you look at group 1A, this is S1. And when you have S1, it still have a chance, it still can accommodate an extra electron. Actually, it is going to be more stable when it is fully filled. And that is why it has a lesser electron affinity in 2A compared to 1A. Now, with the exception of group 5A elements, the electron affinity tends to rise from group 2A all the way to group 7A. And when we have 8A, 8A is what we call the group 18. 8A, this is what we call the noble configuration. So these noble configurations actually do not have to accept any electrons, and they do not give up any electrons. And that's why we are saying that no stable negative ions of the group 8A elements have been found. Now, as one progresses across the period, the electron affinity will increase, of course, except those group 2A and group 5A that we have talked about. And due to the larger attraction from the nucleus, the atom wanting the electron more as it reaches the maximum ability. You remember the effective nuclear attraction increases across the period. because you are actually adding more protons as you go on. But when you look at it down a group, you realize that the electron affinity is going to decrease down a group because the size of the atom is going to increase. And the number of electrons that decrease the stability of the atom, meaning that we are going to have increasing atomic size and also the increasing electron repulsion as you go down a group. That explains why the electron affinity is going to decrease down a group. Now, yes, Mustafa Haden has raised his hand. You can talk.
Yes, bro.
Yes.
Could you please repeat the trend down the group? I've not gotten it clearly.
The trend down a group, we have the electron affinity decreasing. And why does it decrease? One, we have got increasing atomic size. And when we have increasing atomic size, it is also accompanied by the increasing number of electrons. Now, when the atomic size increases, although the atomic size is increasing with the increase in the nuclear charge, that increase in nuclear charge does not effectively counteract the fact that as you go down a group, we have extra nuclear shells being added. And because extra nuclear shells are being added, the size of that atom increases. Now, for you to attract an electron, the effective nuclear charge has to be high. And you have said in the past that the effective nuclear charge decreases down a group. So the amount of energy that reaches the last energy level to be able to attract an extra electron is going to be decreasing as you go down a group, meaning that the electron affinity, the ability of an atom to attract electrons to itself is going to decrease as somebody goes down a group. And again, we are saying that as you go down a group, we have increase in electrons, and these electrons are being added in extra energy levels that are being added. Now, these electrons actually increase what we call electron repulsion. And when there's electron repulsion, then it becomes difficult for an extra electron to be added there. Have I clarified that the student who had asked me to clarify?
Yes.
Thank you. So you can see that the trend is towards more negative affinities from left to right, of course, except those two instances we have said are going to be broken. So here we are looking at a table that is just showing the trend in the electron affinities in the main group elements. And here we are basically looking at the S and the P block elements. Again, you can see here there is a plot of the atomic number and the electron affinity. And you will realize that those that are highest here are the halogens. The group 7A are the ones with the highest. Why? One, they have very high effective nuclear charge. And number two, addition of an extra electron in halogens will actually give a stable noble gas configuration. That is why it is so easy for these elements to attract an electron. What follows here is an exercise. I think if it is not uploaded, I will consult with the daktari so that we can upload this. Now.
Excuse me.
Yes, please.
Can you repeat the second reason why halogens have a higher electron affinity?
It is because the addition of an extra electron will give them a stable or noble gas configuration. They will actually look like the group 8A elements the moment an extra electron is added to them. And therefore, they will easily accept that electron to attain the most stable configuration that we have in the periodic table. Okay, so we now go to what we call electronegativity. Now, when we talk about electronegativity, we are actually talking about the ability of an atom to attract electrons to itself in a chemical bond. And I am going to illustrate this using different species. And for example, when you have hydrogen forming a bond with another hydrogen, these are two atoms of the same element. We know that hydrogen has one electron, the other hydrogen has one electron. Now, when they have one electron, they are not stable. Remember, this is a 1s orbital. A 1s orbital is going to be most stable when it has two electrons. So what do? They can share an electron in the middle here. And when they share the electron, because, you know, this hydrogen here will be trying to attract an electron to itself, while this other hydrogen here will be trying to attract an electron to itself in this chemical bond. But these being atoms of the same element, they have equal abilities to attract electrons to each other, meaning that eventually they will have to share the electrons in the middle here. When they share the electrons in the middle, then we say that what is formed here is non-polar covalent bond. So basically, we say that electronegativity is a measure of the ability of an atom or a molecule to attract electrons to itself in a chemical bond. The type of bond formed is largely determined by the difference in the electronegativity between the atoms involved. So here we are going to have a non-polar covalent bond. Why is it a non-polar covalent bond? It is because these are atoms of the same element, and they have the same ability to attract electrons. You know, when you have two people fighting and these two people are of equal energies, how can you describe that fight? No one is going to win. Yeah? They will just fight and respect each other. But if you look at another scenario here, where you have hydrogen and chlorine, whereby we have the hydrogen chloride gas. Now, here we have hydrogen with one electron, and here we have chlorine with 7 electrons in the outermost energy level. Now, what happens here is this hydrogen here wants one electron to get a full configuration. This chlorine here wants one electron to get full configuration. So what happens in this particular case, this chlorine would try to pull electron, the only one electron from hydrogen, while hydrogen will also try to pull the only one electron from chlorine. Now the question is, these two are atoms of different elements, meaning that they have different tendencies, they have different abilities to attract the electrons to themselves. Chlorine here has a higher ability to attract the electrons, and hydrogen here has a lower ability. So although they are going to form a bond, the sharing of the electrons is going to be such that the electrons are going to be closer to chlorine than they are to hydrogen, because the tendency of chlorine to pull electrons to itself is higher than the tendency of hydrogen. And therefore, if we were to give, yes, Ahmad?
What reason would you give for chlorine having a higher affinity than hydrogen?
It is because of one, chlorine as, are we talking about affinity or electronegativity?
Electronegativity.
Now look at the size of chlorine. Chlorine is a very small atom because of very high effective nuclear charge. And because of very high effective nuclear charge, it means that the force of attraction reaching the valency orbital is very high. And being high, you know, when we talk about effective nuclear charge, we are talking about the positive attraction. So the positive attraction in chlorine reaching the outermost energy level is very high, meaning that it is so easy for it to attract. It has sufficient energy to attract an electron from another molecule. And that is why it has a high electronegativity. It can pull the electron to itself closer than the hydrogen would. And therefore, if we were to draw the shared electrons would be closer to the chlorine than they would be to hydrogen. What does it therefore mean? Yes, there are two students who have raised their hands. Patience, start.
Do you mean chlorine has a high electronegativity or has a high electron affinity?
Both. No, it has high electronegativity.
So we can explain it saying that it has a high electron affinity, being a halogen. Hence, it tends to attract electron more than hydrogen can attract electron.
Yes. The electronegativity is high, the electron affinity is high. When we talk about chlorine, these two aspects are high for both. And when we talk about electron affinity and electronegativity, we have given reasons. One, it is a very small molecule. It is a very small molecule because of the effective nuclear charge. And if the effective nuclear charge is high, then it means that it has a sufficient energy to attract electrons to itself. Okay. Number two, the reason as to why it has a very high electronegativity and electron affinity is that, the acquisition of an electron is going to make it stable. Now, the difference in electronegativity and electron affinity here is this. When you look at it, especially in this scenario, here, this chlorine is trying to attract an electron from hydrogen. But the hydrogen is not letting that electron go. It is also trying to pull an electron from chlorine. So there is a fight. Yeah, there is a fight between the two. And therefore, when we look at the electronegativity of chlorine versus the electronegativity of hydrogen, there are different scenarios that may arise. If the difference is sufficiently high, then an electron is sufficiently or completely transferred from one atom to another. And that is when we have formation of an ionic bond. Now, when the electronegativities are equal, that is when we have formation of non-polar covalent bonds, like when we have two atoms of the same element. But when it is in the middle, then we do have the electrons being closer to the more electronegative element than the less electronegative element. And that means that this chlorine is almost attracting the electron. It is almost taking the electron, but it has not fully taken it. On the other hand, this hydrogen is almost losing the electron, but it has not fully lost it. So what happens here is that this chlorine becomes partially negative because it is almost acquiring an electron, only that it has not fully acquired it. While hydrogen becomes partially negative, partially positive, sorry, because it has almost lost an electron, but it has not lost it. So this is what we call polar covalent bond. Polar covalent bond. But when there's complete transfer of electrons from one species to another, then we have formation of what we call ionic bonds. Now we go on. Moving horizontally across the periodic table, the electronegativity increases. Why does the electronegativity increase as we move across the periodic table? It is because there is increase in the effective nuclear charge. That's why we are saying that due to the stronger attraction that the atoms obtain as the nuclear charge increases. On the other hand, if you are moving down a group, the electronegativity is going to decrease. Why is it decreasing? We have explained it before when we are looking at electron affinities. As you go down a group, the atomic size increases. Therefore, the valence electrons are further away from the nucleus. So due to larger distance between the nucleus and the valence electron shell. So that is why we have decrease in electronegativities as you go down a group. Now, what you have here is a periodic table showing the variation of electronegativities as you move from left to right and from top to bottom of the periodic table. And you can see what happens here. Now, I have mentioned this, when we have ionic bonds, then there is complete transfer of electrons. And this happens when the electronegativity of the two atoms differ significantly. Now, a covalent bond is formed when we have sharing of electrons. And this sharing of electrons can happen such that we have the electrons shared in the middle. If the electrons are shared in the middle, then we have what we call non-polar covalent bond. But when we have a polar covalent bond, this covalent bond is such that the electrons are closer to the more electronegative atom than the less electronegative atom.
A question.
Yes, please.
You said on the ionic bond is we form it when we have two like totally complete different elements. Can it be simply that we are having a metal and a non-metal?
That is exactly where we are heading to. Because you see, when you look at metals, metals are on the left side of the periodic table, and nanometals are on the right side of the periodic table. So you can see that the electronegativities are completely different. So the difference in the electronegativity of the two is going to be very high, and because of that, you are going to have complete transfer of electrons. Okay?
Yeah.
Okay. So when we talk about electronegativity, this is a measure of the ability of an atom or a molecule to draw bonding electrons to itself. This is just another definition. And it is related to ionization energy and electron affinity. So if you look at the discussions of them, you realize that their periodic trends and their explanations have some similarities because one, they depend on the effective nuclear charge. Now, the difference in electronegativity between two atoms in a bond is a rough measure of the bond polarity. That's why it may be non-polar or polar or even ionic. So when the difference is very large, an ionic bond forms because this is where we have a complete transfer of an electron from one species to another. When the difference is large, the bond is polar. But when the difference is small, the bond is non-polar, like in the cases whereby we have two atoms of the same element, like in hydrogen, in chlorine, in nitrogen, all those atoms of the same element have non-polar covalent bonds. And here, what you can see is a summary of what we are talking about. You see, when we have hydrogen here, for example, you realize that the bonding is shared equally. And why is it being shared equally? It is being shared equally because, you know, the electronegativity of one hydrogen is 2.1, the electronegativity of the other is 2.1, and when you get the difference, you are going to get a 0. When you have a difference of 0, then that means, is somebody talking? Yes, Nicholas.
Yes, Prof. Please, can you give us the ranges in the differences? Let's say 0 is non-polar, so from 0 to 7 is polar, then that.
Let me look for that.
Okay.
I think I have it somewhere. I'll be able to share with you. It's somewhere I had. I'll look for it just now and I'll share with you because I have it somewhere. But this is how it is described. Then here you have the formation how those bonds are going to look like, you know. This is actually shown when you look at hybridization. I will look at the content and see whether that is going to be taught. And what follows is an exercise. But let me look for some figures that show what Nicholas is asking for, because I do have them somewhere. Just one moment. I look at I browse through my document here, because I remember I had nitrogen cycle. Just one moment. I have something like that somewhere. This is chemical bonding, electron structure, and chemical bonding. Selectional structures. Just 1 minute. I look for those bond pins. Hybridization. So I can close this. Okay. This is this. Just a moment. Look at this document here, because I think I have them somewhere. So let me stop sharing this so that I can share another document here which has what Nicholas is asking for. So yes, can you see this slide I have shown here? This slide tells us how you can estimate the bond polarities. And atoms with similar electronegativities, if it is between 0 and 0.4, then you have non-polar bonds. And when it is more than 2, you have ionic bonds. But when it is between 0.4 and 2, then you have a polar covalent bonds. These are polar covalent bonds. That's Nicholas, are you getting what? Am I answering your question?
Yes, Prof. Yeah. Thank you very much.
So these are, this is supposed to be polar covalent bonds. So that is how it is supposed to be. If you allow me, I will take the attendance for the other class before the time in the next 5 minutes. Allow me to take the attendance for the other class, so that if there are any other questions now, we can look at them. So I'm taking attendance for the other class students. And here we go. Anita.
Present.
Thank you. Then there is a Nicholas.
Present.
You have just talked to me, so I know you are here. There is the Oboge, Denver.
Present.
Lydia Edosa.
Present.
Then we have Isabella Gardner.
Present.
Then we have Lillian Gishego.
Present.
Then we have Al-Amin Hassan.
Present.
Then Hassan Hasna.
Present.
Then we have Maria Eldin Kisoka.
Present.
Okay, then we have Michelle Mogusu,
Her microphone is not working.
but she's in, eh?
She's present.
Okay. Joy Mushemi.
Present.
Then we have Anastasia Munjuri.
Present. Present.
Then Philip Mutinda.
Present.
Okay. Alice Odiwar.
Present.
Maria Console Patience.
Present.
Kush Rana.
Present.
Sebata.
Present.
Grace Thuku.
Present.
Lorraine Wainaina.
Present.
Njoki Waweru.
Present.
Any student who has not had their name? Okay, so any questions, students? We have about 2 minutes to the end of the lesson. Any questions? Okay, there being no questions, I would like to thank you, students. So we meet next on the Monday. Have a good week. Thank you.
Monday is a holiday.
Monday is a holiday.
Yes.
Which holiday is this?
American independence.
Yeah?
The American independence.
Okay, okay, I stand guided. So Nicholas, you have a question?
Yes, Prof.
Yes.
Please, I don't think we've done ionic radius. I don't think we did that.
You didn't do ionic radius?
I don't think so. We just did atomic radius.
We did the
atomic sizes?
Yeah.
Uh-huh.
But you've not done the ionic.
You have not done ionic?
No, I don't think.
You don't? Okay, that's okay. Yeah. I'll come back to it then the next time we meet.
Okay.
Yeah, I made an assumption that when you were doing about atomic sizes, you know, atomic sizes also goes with ionic sizes, eh?
Yes, Prof.
But that's okay. We will look at it. So thank you, students. You can have a good day.
Thank you, sir.
Okay. Okay.
Thank
bye.
you. Nice meeting you. That was nice meeting you. Thank you.
Thank you. Bye.
Remember to upload this.
I will.